There's a question we haven't quite addressed, and it has to do with molecular formula. Can we use the mass proportions, and in particular the ratios, the small integer ratios that we see in oxides A, B, and C, the 4 to 2 to 1, to write molecular formula immediately? So for example, can we immediately write oxide A as NO4, oxide B as NO2, and oxide C as NO, since we have apparently a 1 chunk to 1 ratio in oxide C, a 2 chunks to 1 in oxide B, and a 4 chunks to 1 in oxide A? We really can't. And the reason why is that we don't actually know that an oxygen atom is 0.57 times as heavy as a nitrogen atom. It could be, for example, 1.14 times as heavy. Let's think about what that would imply in terms of molecular formula. So let's imagine then that an oxygen atom was actually 1.14 times as heavy as a nitrogen atom. So we could say 1.14 times the mass of a nitrogen atom is equal to the mass of an oxygen atom in that case, right? Well, in that case, notice that oxide C is not NO. Oxide C is 2 atoms of nitrogen per 1 atom of oxygen. Oxide B in this case is NO. And oxide A in this case is NO2. Notice that we still have that characteristic ratio of 4 to 2 to 1 actually in the numbers of oxygen atoms. If we think about in oxide C, we'll have half an oxygen atom per atom of nitrogen, right? So we still have the 4 to 2 to 1 ratio built into these formulas. But this is just as reasonable as the apparently simpler idea of just saying, okay, well, it seems like a nitrogen atom is 0.57 times as heavy as an oxygen atom based on the data we've got here, which is going to tell us that oxide C is NO, oxide B is NO2, and oxide A is NO4. Problem is, we don't know which of these two is correct. We don't know what the relative mass of a nitrogen atom is with respect to an oxygen atom. We need more information about atoms in order to answer that question. We need information about relative atomic masses, really. Which of these two mass equations is correct? And what are the masses, really, of a nitrogen atom and an oxygen atom? Now, this might seem a daunting question, particularly when you think about Avogadro's perspective on the issue. Avogadro was living in the late 18th, early 19th century, I believe, and so in his day, massing individual atoms was, of course, out of the question. So what he needed to do was somehow have the ability to count the number of atoms and molecules within a sample. That too seems like a daunting task. I mean, atoms are extremely small and come in extremely huge numbers of particles, right, in a typical macroscopic sample. So it seems like a daunting task. And yet he found a way to do it. And this is why to this day he's known as one of the most brilliant chemists who's ever lived. In the 19th century, he found a way to count atoms. Avogadro's idea was that in a gas, the volume of a gas at constant pressure and temperature is directly proportional to its number of particles. He noticed empirically, experimentally, that volumes of gases held at constant temperature and pressure appear to combine in small integer ratios. So for example, he noticed that 2 liters of hydrogen gas combine with 1 liter of oxygen gas to form 2 liters of water vapor. And so the volumes are reflecting the numbers of particles that are combining, right? If I simply removed the liter label from all 3 of these reagents, well, I have a balanced chemical equation there, right? Same idea for the hydrogen and fluorine example, which I'll let you write out on your own. Just like atoms combine in small integer ratios to form compounds, gases combine in small integer ratios of volumes to form integer volumes of products. And if these two ideas are directly related, as Avogadro surmised that they were, then that means there must be a fixed number of particles in a liter of gas, no matter the identity of the gas. In other words, Consider the bottom case, 1 liter of hydrogen gas plus 1 liter of chlorine gas. If those two are to combine according to the law of conservation of mass to make 2 HCl, then there must be a fixed number of particles in 1 liter of gas. In other words, the ratio of the number of particles in a gas to its volume is a constant. What this means, and the beautiful idea that comes out of this, is that we can use volume to count number of particles. We may not know exactly how many particles there are in a liter of gas, but we don't necessarily need to know, and that was the other powerful insight that came from Avogadro's law. If you've seen the ideal gas law before, this should make sense. With pressure and temperature constant for an ideal gas, N over V is going to be a constant ratio, or the inverse of the molar volume, which is the volume per number of particles, essentially, for a gas. So here it is again, restated at the top of the slide. At constant temperature and pressure, gas volume is linearly related to the number of gas particles, or volume counts the number of gas particles. Experimentally, here's what we find for the 3 gases that we've been looking at so far. When we combine 1 liter of nitrogen gas and 2 liters of oxygen gas, we get 2 liters of oxide A in particular. When we combine 1 liter of nitrogen gas with 1 liter of oxygen gas, we get 2 liters of oxide B. And when we combine 2 liters of nitrogen gas with 1 liter of oxygen gas, we again get 2 liters of oxide C. But now we can treat these volumes of combining reactants just like a number of particles, since the ratio of volume to number of particles is a constant. So I can literally cross off the volumes here, and now I have a number of particles on the left, a number of atoms, that has to add up to the total number of atoms on the product side. And so I've got 2 of each type of oxide on the product side, and so I can immediately say from this that, all right, oxide A must be into 2 nitrogens and 4 oxygens. 2 copies of that means that oxide A has got to be NO2, right? I'm making 2 NO2s for a total of 2 nitrogen atoms and 4 oxygen atoms from 1 N2 molecule and 2 O2 molecules. Balanced chemical equation, right? We can do the same dance with oxide B. 2 nitrogen atoms and 2 oxygen atoms combine to make 2 molecules of oxide B. To balance it, oxide B must be NO. We could also conclude that from the mass ratios in blue that you see in the bottom right here. If the ratio of oxygen is 4:2 in A to B, then we must have half as many oxygen atoms per nitrogen in oxide B. And indeed we see that. We've got 1 in oxide B and 2 in oxide A. And finally in oxide C, we do the same dance once again. 4 atoms of nitrogen and 2 atoms of oxygen to make 2 molecules of oxide C. So in this case now, we have 2 nitrogens per oxygen for a molecular formula of N2O. Before we move on, I just want to impress on you the power of this idea. The idea that we can treat volume as a way to count number of particles. And even though Avogadro had probably a feeling that the number of particles was just astronomical, he also understood that he didn't really need to know how many particles there were in a liter of gas. As long as he understood it was the same for every gas, and therefore we could use it to count number of particles in a relative way that allowed us to come to molecular formulas. Now that we have these molecular formulas, we can return to the mass data to think about relative atomic masses. And in particular, I want to draw your attention to the oxide B line here. See that on the oxide B line, which is 1 atom of N for every atom of oxygen, we have 1.14 grams of oxygen for every 1 gram of nitrogen. That means that the relative masses of nitrogen and oxygen must be 1 to 1.14. I have it backwards on the slide, but the mass of an oxygen atom is 1.14 times as heavy as a nitrogen atom. We can repeat this same type of experiment for a huge number of compounds of 2 different elements to develop an entire table of the relative atomic masses of all the different elements. Out pops the periodic table. The masses that you see under each element are the masses relative to a standard unit of atomic mass called the atomic mass unit. So instead of saying that nitrogen has a mass of 1 and oxygen a mass of 1.14, we say that nitrogen has a mass of basically 14 and oxygen a mass of basically 16. And if you check on a calculator or what have you, the quotient 16 over 14, you'll get pretty close to that 1.14 target. The standard is chosen because of the particles within the atom, and we'll talk more about that in a future video. But you should notice that the smallest element, hydrogen, has a mass of basically 1 atomic mass unit, and the other elements are expressed as ratios of the mass of a hydrogen atom. So to summarize, we've seen that the elements combine in definite proportions to form compounds. The mass proportions of two elements in different compounds reflect small integer ratios. That's the law of multiple proportions. And the first point is the law of definite proportions. These three ideas, conservation of mass, definite proportions, and multiple proportions, are the experimental or empirical basis for the atomic molecular theory, the critical idea that matter is made of atoms. While that theory is interesting in its own right, to really develop a quantitative understanding of how atoms combine to form molecules and elements combine to form compounds, we really need to know the relative atomic masses. And using Avogadro's law, this idea that the number of particles in a particular volume of gas is a constant regardless of the identity of the gas, we can actually use volume to count numbers of particles and to determine relative atomic masses. And from there, by repeating these kinds of experiments with a variety of compounds, of a variety of pairs of elements, we can flesh out the entire periodic table's worth of relative atomic masses.